Hi everyone, my name is Dron and I'm a 16-year-old high school student based in Ontario, Canada. And I'm super interested in the intersection of math, music, and technology. Interesting fact, I was actually born in Cyprus, so I've always been close to the Mediterranean. And I'm really excited to give this talk today. What I want to talk to you about is actually about AI composing music. So I personally love to compose music in my free time, but it turns out that AI likes to do it as well. And it's not immediately obvious why. After all, music is like a very human and creative component, right? So I want to talk to you about how we can use AI to generate music. Why do we care about having AI generate music? To look at an example, this is the Bach Google Doodle, and it received over 50 million queries in just 3 days. Now what it does is it takes a simple melody and harmonizes it into the style of a Bach chorale. It's not immediately obvious that people would care about it, but clearly people do. It allowed people to express themselves and it gave them a new toy in musical self-expression. So what if we were able to give everyone the ability to express themselves at the same level as trained musicians like the Berlin Philharmonic? So there are kind of two kinds of generative modeling in music. We have symbolic generation and raw audio generation, and I'll get into what those mean. With symbolic generation, we essentially have some kind of abstract representation of what music actually is. So when Beethoven wrote his music, he actually wrote out sheet music. He obviously wasn't producing the sounds of a violinist or a flautist. Instead, though, he was writing instructions so that when a musician will read those, he will be able to express those and interpret those and create audio out of it. And so we can do a similar thing with data. We can represent music as data as maybe a pitch time with a start time, end time, and a volume level. And we have the last representation, which is the most direct, which is actual raw audio. So we can listen to what this abstract sample sounds like. So how can we begin to model these with AI? Well, a very classical approach is with recurrent neural networks, which is essentially where we try and predict the next step based on all the previous steps that have come before it. And this is a very classic approach where it's even in intro to deep learning courses now. The issue is, though, is a lack of structure. There's no rhyme or reason to what the AI will play. It's simply predicting the likeliest next step. So it almost sounds like a kid at a piano just playing and playing and playing, but without any rhyme or reason. So clearly, we're nowhere near the Berlin Philharmonic. So how can we add a more human element to it? That's what performance RNN tries to do. It essentially tries to remove the robotic, quantized nature of the abstraction into more of what a musician's interpretation would sound like. You can listen to an example here. Yeah, so what we can see, or hear, is essentially that the musician is taking this high-level representation and bringing out the expression and feeling behind it. So how do we model this with AI? Well, one of the major problems of recurrent neural networks, and MIDI in general, is that it's very, very fixed. That it has to tell each time, yet each time step, it's going to say, okay, all the notes you are holding, hold them again. And the model has to learn how to do that, which is a big waste of model capacity. So instead, what performance RNN does is it switches to an event-based structure, allowing for different node-on and node-off events, allowing for a much more compressed representation. This allows us to have like time shift events, where the AI can actually expressively model where exactly it will place the note. And this allows the AI to be very, very expressive. But it's still not quite enough. To get to the next level, we need to use transformers. I'm sure you've heard of what a transformer is, but it's essentially getting rid of the recurrent nature of the RNN and using a self-attention mechanism. And we can kind of visualize this in terms of music through Magenta's music transformer. So if we look at this quick video clip, so each of those circles essentially marks a relationship where the AI is actually drawing from that section of thematic material. And so what we see is that this underlying structure of themes and motives is starting to come out, and it's starting to sound actually human. And this is a huge development. So let's listen to some more examples. So clearly Music Transformer is very, very powerful. It can generate melodies with long-term structure and with motives and with harmony and melody. So it's clearly getting there. So why aren't we close to the Berlin Philharmonic yet? Well, it's actually because of one reason: timbre. You see, with a piano note, there are only really three factors that you need to consider. You have which note you're pressing, how long you're pressing it for, and how hard you're pressing it. But with something like a violin or a flute, there's a huge amount of variation in tone color or slight changes in articulation, and those things make a huge difference, but AI can't really capture it right now. So what's limiting us? It's probably the symbols, right? Because we can't really accurately represent such articulations in data. So what if we just get rid of the middleman? That's what WaveNet tries to do. Essentially what WaveNet does is it works directly with the waveform audio, so that directly the audio we hear, and it models that. And it's actually mostly used for text-to-speech synthesis, where it gains very good results. But it was actually tested for music too, and you can take a listen. You can tell that WaveNet is still at the RNN stage here, because it doesn't have a lot of long-term structure. It just feels like it's noodling around like a kid at the piano. But why is that? I mean, the dilated convolutions that WaveNet uses should allow for it to grow its receptive field, right? Well, the reality is that a model needs to be trained on samples that are as big as the longest correlations that you want to model. Raw audio contains so much information that even on the scale of a second, you're already dealing with sequences of almost 16,000 steps. So it's very difficult to model even 10 or 100-second things, let alone 10-minute pieces. So the primary issue and the primary chasm we have to cross in raw audio music generation is just the ability to get around this information density. And I want to go over two approaches today. One of them is the hierarchical WaveNet approach. Essentially what this will do is that it'll have a WaveNet that will generate the raw audio, so the low-level details, but it'll also have an encoder that will try and generate this high-level representation that it'll pass to the next WaveNet on top of it. And this will continue on and on and on. So essentially what we get is one WaveNet that is trying to model all the low-level stuff, next WaveNet that is trying to model maybe medium-range correlations, and the next model up, which is trying to model higher-level correlations, and so on and so on. And the idea is to gain long-term structure in the top models while still retaining the low-level quality from the bottom models. Another approach is essentially an approach called wave to MIDI to wave. And this is really interesting. Essentially what it's trying to do is it's taking real audio files, transcribing them into MIDI so that we can work with them symbolically, and then by taking the MIDI that the model is going to generate, we're going to use a conditional WaveNet, so a WaveNet conditioned with the MIDI input, to actually create this new raw audio. And you can take a listen to how it sounds. Essentially, this gets around our raw audio information density problem by converting it into our abstractions, so MIDI, and modeling that MIDI symbolically, and then again taking that MIDI and putting it back into raw audio. Now again, this suffers from the same limitations that it can only accurately describe piano and some other instruments. But this approach could still see a lot of development in the future, especially if we can develop better and more compact abstractions that are able to actually represent saxophone or violin or flute much better. So now I want to go over a quick use case. So recently I developed a web app called Intellier, and essentially what it does is it uses generative models to generate lots of melodies for musicians to be able to practice listening to them and playing it back. And even the scoring algorithm is done by AI. And essentially what this shows is just a mini application of showing how powerful generative models can be even in a very primitive state. So hopefully I've piqued your curiosity and interest in this burgeoning field, and it's far from solved and there's many different problems that are open, and hopefully I've convinced you that maybe Robobot is not as far as we might have initially thought. Thank you for listening.